Alright, here we go with the Chapter 8 Homework A review. First of two Chapter 8 assignments dealing primarily with the ideal gas law and a few applications of it. Our average did bounce back a bit this week, so we were up above 10 out of 12, so it's a pretty good outcome overall in this assignment. But I am going to go through 10 questions that I primarily identified from the results in Blackboard as being ones that we didn't do as well on, as well as one or two of these that are requests from a student. Alright, so let's get right into it, and we're going to first talk about measurement of pressure. So this is the topic we covered at the very beginning, where we talked about the different devices for measuring pressure and how they work. And this first one deals with a barometer. So it doesn't specifically use the word barometer, but that's kind of what we're talking about. So it says a certain pressure supports a 256 millimeter high column of mercury. How high a column of water would it produce? Would it support? The density of mercury is 13.6 grams per cubic centimeter. Now, this is something that we discussed a little bit in class, although I did not go through the math for it. So this was kind of left to you to figure out on your own. And this was a pretty tricky question to figure out on your own, if I'm being honest. So, if you didn't quite get this one, don't worry about it. It's certainly a step above what we covered in our lectures. But we talked about how we use mercury for barometers and manometers because it's so dense, and so you can measure, pretty reasonable, normal human pressures without using a really huge, long column of the liquid. So for mercury, as we said, atmospheric pressure is 760 millimeters, which is about 3 feet tall at the most, or probably 2 feet tall. And if we were to use water, it'd have to be a few stories tall, 30 feet or so. And we didn't go through the math for that, but this is what this question is asking you to do. So it says a certain pressure supports a 256 millimeter high column of mercury. How high a column of water would it support? All right, so what we're going to do here, and the density is important, it is given to you here, and that's going to come into play. So the first thing to realize is that, remember that the definition of pressure is force divided by area. All right? And when you have a barometer or a manometer, what you're basically having, let's draw it for a barometer here. So you have a sort of a bowl of the liquid, and then a tube inverted in that liquid, and it's going to be pushed down by the air, and it's going to rise up so high into the tube. And so basically what happens is you have two forces opposing each other that have to be equal. You have the pressure of the air that's pushing the liquid up into the tube, and then the weight of the liquid in the tube pushing down. And those two forces balance each other. So what it basically works out to is, in this pressure equals force over area, the force that's being exerted can be also written as the mass times the gravitational constant g, or the weight of the liquid in the column. So basically the weight of the liquid in the column opposes the air pressure, and that's when they completely balance each other. Now the other thing that we can do here is we can rewrite the area. So again, it's force divided by area. Area is the size of the area that the force is pushing down on. But remember from geometry, the volume of anything is going to be the area times the height. So if you have a column with a certain height, here the volume of the liquid in there is going to be the area times the height, meaning that the area can be rewritten as the volume divided by the height. So we're going to make that substitution here. So we're going to replace area with the volume divided by the height, and that's where the height comes into play, because as we said, we're trying to figure out how high of a column we're talking about here. And then this can be rewritten as mgh divided by v. Okay, so we're just moving this height to the numerator. Okay, so that's going to be sort of a measure of pressure in terms of the mass of the liquid that's in the column, the gravitational constant g, the height of the column, and the volume of the column that the liquid occupies. And another important thing to realize is that mass divided by volume is equal to the density. So that's the definition of density. So that's where density is going to come in. We're going to replace mass over volume with density. So what we finally get is a formula for pressure in terms of the properties of the liquid that's in the measuring column, which is the density of the liquid, m over v, times the gravitational constant g, times the height of the column. And so this is going to then dictate the relationship between the density of the liquid and the height of the column. And so then what we can do, G is a constant here, and so what that means is that density times height is equal to 1 over G, which is a constant. And so if we're comparing two columns of liquid that are measuring pressure, we can write a relationship that D1H1 equals D2H2. In other words, the density of the liquid and the height of the column are inversely related, and so we can set up this relationship here. So that was kind of a long derivation to how we got there, but the key concept is that the more dense the liquid, the shorter the column that will be supported, the less dense the liquid, the higher the column. So what we're looking for here is the height. So let's say that H1, this is the height of the mercury column, and D1 is the density of mercury, and we're looking for H2, which is the height of the water column. So H2 is going to be D1H1 over D2, where D2 is the density of water. And so what we have here then is just we have to put the numbers in. So D1 is the density of mercury, 13.6 grams per cubic centimeter. H1 is the height of the mercury column, which is 256 millimeters. And then finally D2 is the density of water, which is 1.0 grams per cubic centimeter. So what we come up with in this for the height of the water column in millimeters is just 13.6 times 256, which is 3,481.6 millimeters. Now the annoying part about this question, well the next annoying part about it is that all the answers are in different units. So for millimeters we have them in inches and feet. So in inches we're going to take that number and divide it by 25.4 to get it to from millimeters to inches. So this is 137. We'll just keep three significant figures like all the answers. That's 137 inches. That doesn't match any of the answer choices. Then we divide that by 12 to get it to feet, and that comes out to 11.4 feet. Alright. So that would be answer choice D. So we had to also convert it into the two different units, inches and feet, to be able to get that. Alternatively, we could have converted H1 here, the height of the mercury column, into inches first, and then we could have solved directly for inches. So there's a couple ways of doing that, but you have to get to the right units as well for this problem. But 11.4 feet is the correct answer, and that's one of our choices there, D. So this is not the most important concept. We don't really measure pressure, using water columns, and this is why, because we need really tall columns to do that, taller than a basketball hoop, just to measure, a pressure of 256 millimeters of mercury, which is pretty low. But anyway, this goes through the math behind that, and it's kind of more of just a interesting type of problem, not one that's necessarily going to be a big point of emphasis on any exams we have. Now the next question here was sort of a more typical one about measuring barometric pressure and atmospheric pressure and things of that. So here it says the barometric pressure was 1.05 atmosphere when the mercury level in an open-ended manometer connected to a flask of gas was 126 millimeters higher on the side open to the atmosphere than on the flask side. What was the pressure of the gas in torr? And it says hints against the apparatus. Okay, so in these types of problems here, we're talking about measuring pressure with a manometer, which is a closed sample, and there's two kinds, open-end and closed-end. So this we're saying is an open-end manometer on the side open to the atmosphere, or it's directly said is open-end manometer. So what you have is a sample of gas, then you have a U-shaped tube, and one end of the tube is open to air. And so basically on this end you have the pressure of the air pushing down, which is the barometric pressure. So that number is 1.05 atmosphere. That's the barometric pressure pushing down on that side. Then you have the pressure of the gas pushing in the other direction, and we're telling you here that the mercury level connected to the flask is 126 millimeters higher on the side open to the atmosphere. So it's going to look like this. Your mercury level is going to be higher over here than there. So it's higher on the side open to the atmosphere. And this is the difference in height here, is 126 millimeters. Okay, now what this all means is, again, think about it a little bit conceptually before we start plugging in numbers. If the mercury level is lower on the side connected to the gas and higher on the side that's open to the air, that means the pressure of the gas is pushing harder than the pressure of the air that's opposing it. And that's why we create the balance in this way. It's pushing harder, so this goes down further on this side than it does on that side. And that means our gas pressure is going to be atmospheric pressure plus the difference in height. So when you're using an open-ended manometer, it can be plus or minus delta H, and again, that depends on which side is higher. So if the manometer is higher on the side connected to air and lower on the side connected to the gas, that means the gas pressure is higher by that amount. So now to do this, we're looking for pressures in torr, which is the same as millimeters of mercury, so we need to convert everything to millimeters of mercury. So the atmospheric pressure is 1.05 atmospheres. We have to convert that to torr or millimeters of mercury first, so multiply by 760. So in atmospheres, in torr, the atmospheric pressure is 798. And then the gas pressure is just going to be that, 798 torr, which is atmospheric pressure, plus the difference in height, which is 126 millimeters or 126 torr. Those two units, as we said, are equivalent. So we add 126 to that and get 924. So that means in this sample of gas, the pressure is 126 torr higher than atmosphere, which comes out to 924. So those are two questions on measurement of pressure. Again, not really a huge story because it's not really dealing with chemistry at all in reality, but just to give you some background on how that's done. Now the rest of these are going to deal with the ideal gas equation in some form, which as I said is the major topic in this chapter. So the first question here is, suppose that 7.88 times 10 to the minus third moles of hydrogen occupies a 256 milliliter container at 28 Celsius. What is the pressure in torr? So in this problem here, we don't have changing conditions. We don't have the volume or the pressure or the temperature or the number of moles changing. It's just one sample of gas. And so in this one here, it's just a typical problem where we're going to just use PV equals nRT. That's going to be the starting point in pretty much all of these problems. But here again, we don't have different conditions before and after or some change in any of the conditions. It's just one set of conditions, and all we're solving for is the pressure P. So we're solving for pressure, which is nRT divided by V, and we have here the number of moles, which is N, the volume V, and the temperature T. We have all the rest of those except for pressure. We're just going to solve for it. Now again, in problems like this though, one of the keys is units, so we have to make sure we do this. So when we put the numbers in, N is number of moles. That's just going to be in moles, of course. There's no real trick there with units. But then R, we're going to use the typical universal gas constant, which it can be in different units, but the one that we're going to use is going to be this one here, 0.0821 liter atmospheres per k mole. And this tells us what units we need for everything else. So temperature needs to be in Kelvin and volume needs to be in liters. So our temperature is not given in Kelvin, it's given in Celsius. So we have to make that conversion there, 28 degrees Celsius plus 273 to get it into Kelvin. It's 301. So we're going to use 301 Kelvin for the temperature. And then we're going to divide that by the volume, which has to be in liters. So the volume is 256 milliliters, which is equal to 0.256 liters. So when we put those in, we're going to get the pressure. So give me 1 second to calculate that. So what I got for this was 0.761, but again, paying close attention to units, that's atmospheres. And this wants it in torr, so we're going to multiply that by 760 torr per atmosphere. So that's the most common pressure conversion unit we have to do. So when we multiply that number by 760, we'll get 578 torr as our pressure. Alright, so there was a few unit conversions here. We had to take temperature into Kelvin, volume into liters, and then once we got our pressure, we had to do one more conversion to get it into torr. So this is again a type of problem where we're just using PV equals nRT and solving for whichever of those parameters is unknown. Now the next few here are going to deal with situations where the conditions for a gas is changing. We're changing the temperature, the volume, or both, or pressure, something's changing about it. And we're still going to use PV equals nRT as our starting point, but in most cases we're not going to look at changes for all of those parameters. It's just going to be one or two of them that are changing, or well, at least two of them, I suppose. All right, so here we have a 23.2 liter sample of dry air, which means that it doesn't have any water in it, basically. And it's cooled from 89 Celsius to 17 Celsius. While the pressure is maintained at 2.85 atmospheres, what is the final volume in liters? So in this problem here, we always want to start with PV equals nRT. There are individual equations for a lot of these gas laws. This one would be Charles's law if we're trying to think about it in those terms. But we don't need to remember all the individual equations to be able to do this. We start with PV equals nRT, and we're going to find which of those parameters, which of those quantities is changing, which ones are constant, and move all those to one side. All right, so in this problem here, we're changing the temperature, so that one's definitely changing. And we're asking for the final volume, so volume is going to be changing. But we're not telling you anything about how much gas we have, so we're going to assume it's the same amount of gas in both cases. Number of moles is the same. And also, we gave you a numerical value for pressure, so we could account for that, but the pressure is maintained at 2.85 atmospheres. That means the pressure is not changing. So even though we have a number for it, and even though we could put that number in and solve the equation using this number as part of the answer, it's not changing, so in reality it doesn't need to be included. It's one of our constants. So when we move everything that's constant over to one side, volume and temperature are changing, everything else is constant, so we're going to have volume divided by temperature is equal to nR divided by P. And again, these are all constant. And so that means we can write a relationship involving volume and temperature where V1 over T1 equals V2 over T2, which, as we said, this is the mathematical expression for Charles's law. And so what we're solving for here is V2, the final volume, so that's going to be V1 times T2 over T1. Those units are directly related to each other. And so now we can just plug things in. But for problems like this, we can use whatever unit we want for volume. That's going to give us the answers unit for V2. But we have to make sure that temperature is always in Kelvin. So for gas law problems, I've emphasized it a few times already, temperatures have to be in Kelvin. There's no negotiation on that. You can't use Celsius to get the wrong answer. So T2 is the final temperature, which is 17, and T1 is 89. So we have to convert each of those to Kelvin by adding 273. So the final temperature is 17, which plus 273 is 290. So our final temperature is 290 Kelvin. And then our initial temperature was 89 Celsius, which in Kelvin we can add 273 to that, 362. Alright, so our temperature is getting smaller, which means that our volume should get smaller as well, and that's what will come out here when we do this. But if you do not convert your temperatures into Kelvin, you would get an answer that's wrong, but much smaller than it should be. So what we get for this is 18.6 liters. So a small decrease in volume, not a huge decrease, but it does respond to the temperature. That comes out to 18.6. But again, you have to make sure your temperatures are in Kelvin for that to work. Alright, so that was an ideal gas law problem where one of those parameters was changing. And then here's another one that's actually quite similar, but this time it's something else that's constant. So we have a balloon filled with helium. Volume is 1.5 liters, pressure 90.5 kPa. That's one of our other pressure units which we don't use as often. And the temperature is 25 degrees Celsius. What will the volume of the balloon be at a pressure of 35 kPa? So we're reducing the pressure if there is no change in temperature. So again, we gave you the temperature here, so you could include that in the relationship that you're going to use for this problem, the equation you're going to use, but it's constant, so it doesn't need to be there. Anything that's constant can be left out, even if you know what the value is. So again, starting with PV equals nRT, in this case, the ones that are constant are N in number of moles. It's a balloon, so as long as the balloon's not leaking, there's going to be the same number of moles. And we're not telling you how many moles there are, so we're going to assume that's constant. R is always constant here. So basically it's already set up where the two units that are changing are pressure and volume. We're telling you the pressure changed, and we're asking you for the final volume again. And so we're just going to write this in this way. And so the ones that are changing are pressure and volume, which means we have this relationship, P1V1 equals P2V2. We introduced this in class as Boyle's law. You should know that this is a Boyle's law situation. But again, you don't have to always remember the equations because they all come from the same ideal gas equation. So P1V1 equals P2V2, and here we're going to solve again for final volume, V2. In this case, it's going to be P1 times V1 over P2. Alright, so the initial pressure is 90.5 kPa. We can use whatever pressure units we want as long as they're the same. So 90.5 kilopascals. The initial volume is 1.50 liters. And the final pressure, P2, is 35 kilopascals. Alright, so again, as long as the two pressure units are the same, they'll divide out. That'll give us an answer in liters. And that comes out to 3.88. So the volume gets bigger because the pressure gets smaller. And it is helpful for a lot of these to, especially if it's just a situation where only two of them are changing. Last time it was volume and temperature, this one it was pressure and volume. For those types of problems, it is helpful to think conceptually about the videos I showed in class really that illustrate how the different things change. So we should recognize conceptually that if the pressure gets lower, the volume should get larger. Remember the demonstration that I showed, the video I showed in class where they had a balloon inside of a vacuum chamber. They lowered the pressure inside the chamber and the balloon got bigger. So those two should respond in that way. In this case, the pressure is dropping and the volume is getting bigger, so at least the answer makes sense, even if numerically it's also correct as well. All right, and then the next question here is a similar one, but this time three things are changing, not just two of those quantities. Three of them are. So here again, we're calculating the volume. So we're solving for a volume at 43 Celsius and 565 torr if it occupies 12.7 liters at 295 Kelvin and 325 torr. So here looks like we're changing pressure, volume, and temperature. So it's the same sample of gas. So again, number of moles is constant, but here we have two different temperatures, 43 Celsius, 295. So in Kelvin, which we need to convert to, 43 Celsius plus 273 is 316. So the temperature is changing. It's going from 316 to 295. And the pressure is changing as well, 565 and 325. And so both of those are, so two things are changing, really all three are, because that means the volume will also respond. So when we start with PV equals nRT in this case, the only constants here are the number of moles and R. When we rewrite this, we get PV divided by T equals nR, and that's going to be constant. And so the relationship we're going to derive for this one is a combined equation that combines Boyle's law and Charles' law together in reality. But again, it comes directly from here, PV over T, so P1V1 over T1 equals P2V2 over T2. Okay, so those are going to be what we're going to be using. Which ones we call P1V1 T1 and P2V2 T2 is arbitrary. Usually I like to use the ones that are completely given to us as 1, and the one that we're solving for is 2, but that's up to you. So if we call this V1 and this T1 and this P1, this would be T2, this would be P2, and we're solving for V2. So if we rearrange this, where we call V2 our unknown volume, it's going to be P1, V1, T2 over P2, T1. So the algebra is a little bit more complicated when you have three things. You have to make sure you do that part right. So let's see, make sure I did that. V2 is going to be P1 over P2, V1, and then T2 over T1. So that looks correct. So now we can just put the numbers in. And again, for pressure and volume, it doesn't matter what units you use as long as you're consistent, but temperature has to be in Kelvin, so that's why we converted that second temperature into Kelvin there. Alright, so when we put the numbers in, P1 is the initial pressure, which we called 325 torr. V1 is the initial volume, which is 12.7 liters. And then we have T2 in the numerator, which is our 316 Kelvin, the temperature that's associated with our unknown volume. And then in the denominator we have P2, which is 565, so the pressure is increasing. And then the first temperature, T1, is in the denominator, and that's 295 Kelvin. Alright, so in problems like this, it's more critical to make sure that you do the algebra right. It's a little bit harder to think about conceptually, so you have to make sure you're getting the numbers in the right place, and that you're also, of course, consistent with units. So as long as temperatures in Kelvin, anything else is fair game. And so what I got was, if I did this correctly, 7.82 liters. Alright, so we have sort of opposing things here because the temperature is getting higher, which would increase the volume, but the pressure is getting lower, the pressure is getting higher, which would increase the volume, and the temperature is getting higher, which would decrease, but anyway, in that it's a decrease in volume of 7.82 liters. I think I botched how I said that again, so I'm not going to try. But nonetheless, that should be numerically correct as long as I didn't mess up my math, and this is the approach you're going to want to follow for this problem. Alright, so that's the last one I think that deals with directly just PV equals nRT, but the last few we're going to do are also going to start with that as kind of our initial basis. So here we're talking about gas density. So this is a typical density, grams per liter, which is mass over volume, the sort of standard definition of density we use. And we're just looking for the density of this gas, CFCl3, at 32 degrees Celsius and 1.56 atmospheres. So we derived an equation for density in class, and I'll derive it here quickly again. So we start with PV equals nRT, and what we're going to do is we're going to replace N, which is number of moles, with the mass divided by the molar mass. So that's a definition for number of moles that we learned back in chapter 5 in terms of the mass of the compound or the mass of the substance, mass divided by molar mass. So we make that substitution. And then what we're going to do is we're going to solve for mass divided by volume because density is equal to mass over volume. So if we rearrange this equation and put mass over volume on one side, what we end up with on the other side is pressure times molar mass divided by RT. So this is the equation for density of a gas in terms of mass over volume, grams per liter. Alright? And so that's all we have to use is that equation here. So the density of this gas is the pressure, which is 1.56 atmosphere. So here we are using R, so your pressure does have to be in atmospheres for the units to work out. So 1.56 atmospheres, that one we didn't have to change. And then the molar mass we need of this gas as well. So the molar mass for CFCl3 is just carbon plus fluorine plus 3 chlorines. So I'm not going to go through that, but calculating molar mass is something we should be pretty good at now. So 12.01 for carbon, 19 for fluorine, and 3 times 35.45. So I got 137.36 grams per mole is the molar mass. So we'll put that directly into here. And then that's going to be divided by RT. So R is 0.0821 liter atmospheres per K mole. And then T in this case has to be in Kelvin. So it's 32 Celsius. So we need to add 273 to that. It should be 305. Yeah, 305 Kelvin. So we need to make sure temperature is also in Kelvin for all these types of problems. Alright, and so what that leaves us with is atmospheres canceling out, moles canceling out, Kelvin canceling out, and that gives us a density in grams per liter. Alright, so numerically what this comes out to is I got 8.56 grams per liter. That number seems big. Let me check. It's not abnormally huge, but let me make sure that's right. Yep, comes out the same. So 8.56 grams per liter for the density of this gas. It does scale with molecular weight, so the heavier the gas, this is a fairly heavy gas in terms of its molar mass, the higher the density will be under the same conditions, and so that's what we get for that one. Now, this question here deals with a different density unit, which I didn't exactly cover in class, but which is called molar density. So molar density is, regular density, or what's called gravimetric density sometimes, is grams per liter. Molar density is just the ratio of moles per liter. So it's how many moles occupy 1 liter for that gas. And you can, in principle, you can calculate molar density for liquids as well, but we're going to do it here for gases, of course. So here it says, on a certain winter day in Montana, the average atmospheric pressure is 747 torr. What is the molar density of air when the temperature is 17 Celsius? Use decimal format to not type the answers. So here we're starting with PV equals nRT, but we actually don't need to rearrange anything or replace any of the units. We're just solving for molar density, which is moles per liter. So what we're solving for here is N divided by V, moles divided by volume, and then we're going to just rearrange that. So here are the units for molar density, moles per liter, sort of cued us in on what we need to do. We need to take the moles and divide it by the volume. So that ratio, N divided by V, is equal to pressure divided by RT, P over RT. So we're just solving for this ratio here. We don't know the individual values. We don't know how many moles of gas we're talking about. We don't know what volume of gas we're talking about, but we can get the ratio N divided by V is a function of just pressure and temperature. So for that, we can go ahead and just put the numbers in. So this calculation is going to involve R, so our pressure needs to be in atmospheres. So it's 747 torr, and then 1 atmosphere is 760 torr. So the pressure in atmospheres is 0.983. And then RT in the denominator. So R is the universal gas constant. And that's why we had to have pressure in atmospheres, so those units work out. And then temperature has to be in Kelvin. 17 Celsius plus 273 is 290 Kelvin. Alright, so that's all it's going to be, is just those 3 numbers there. So what I got was 0.0413 moles per liter. Alright, atmospheres cancel out, Kelvin cancels out, and we're left with liters per mole in the denominator, which is moles per liter when you move that up to the numerator. So 0.0413. That means 1 liter of this air in these conditions has 0.0413 moles of gas in it. Or alternatively, the reciprocal of that would be the volume of 1 mole of air. So that would be 24.2 under these conditions. So the reciprocal of this would give you the molar volume. So this is the molar density, which is moles per liter. The reciprocal of that is called molar volume, which is liters per mole. So anyway, those two related parameters can be found using just the ideal gas equation and rearranging and solving for what you're looking for, which is, in this case, moles divided by volume. Alright, so that one was a little bit different concept. We didn't introduce that in class, but I think with unit analysis you can get there. The last 2 problems I'll go over deal with gas stoichiometry. So both of these are going to involve PV equals nRT, but then we're going to combine that with a stoichiometry problem. So here we say that chlorine gas can be prepared in the laboratory by the reaction of manganese dioxide with hydrochloric acid. So the reaction is shown here, and it is balanced already, so we don't need to do any balancing. How much MnO2, and I believe that the answers were in grams, I didn't save the answer choices here, but how much MnO2 should be reacted with excess HCl to obtain 275 milliliters of chlorine gas at 5 Celsius and 650 milliliters of mercury? So in problems like this, what we're typically going to do, so for this one, this is a gas. We're giving you the volume, the temperature, and the pressure. And so we're trying to figure out then for those conditions, how much of this reactant do we need? Alright, so this is a bit of an involved problem because it really involves 2 steps. The first thing we're going to do is we're going to use PV equals nRT to find out how many moles of this gaseous product we're producing. So for any of the reactants and products that are gases, which in this case is only the Cl2, we can use PV equals nRT to relate the number of moles to the volume, temperature, and pressure. And so that's exactly what we're going to do here. PV equals nRT, and for Cl2, which is our gas product, we're going to solve for number of moles by just taking pressure times volume over RT. And this is going to use R, so we have to make sure that pressure is in atmospheres, volume is in liters, temperature is in Kelvin, so we have some conversions to do. But anyway, what we end up with is the pressure is 650 millimeters of mercury, so we divide that by 760, so the pressure in atmospheres is going to be 650 millimeters of mercury, that's the given pressure, and then 1 atmosphere is 760 millimeters. And that comes out to 0.8 855 atmospheres is our pressure. The volume was 275 milliliters. We can convert that to liters in our head. That's 0.275. And then we have RT in the bottom. So R is the universal gas constant. And then temperature is 5 degrees Celsius. So 5 plus 273 is 278. That's the temperature in Kelvin. So with the gaseous product Cl2, we can use PV equals nRT to figure out how many moles of that product formed. And so what I got was 0.0103 moles of that gas formed. So we know how much product is formed. Now we're just trying to figure out how much MnO2 we need to form that much product. So it becomes a stoichiometry problem. And I believe the answers we were looking for were in grams of manganese oxide. So we're looking for the grams of MnO2. We're forming 0.0103 moles of Cl2. And then using stoichiometry, we know that the coefficients for both of those are 1. So for every mole of Cl2, we're going to require 1 mole of manganese dioxide, MnO2. Manganese fluoroxide is a more technical name for that. So that's how many moles of MnO2 we need, and then we just have to use its molar mass to find how many grams that would be. So let me get that real quick. I don't remember the atomic mass for manganese. It's 58.93, 54.94. Alright, so manganese and 2 oxygens, 54.94. 32. So the molar mass of this is 86.94 grams per mole. And that comes out to 0.895 grams. So I think this was a multiple choice question. I just didn't put the answer choices in to save myself some space. But whatever it is, it should be looking for it in grams, and that's just a stoichiometry problem once you figure out how many moles of Cl2 you have. So this is how many moles of Cl2 we have. It's the gas phase product that we're forming at that given temperature, volume, and pressure, and then from there, it's stoichiometry to figure out grams of MnO2 that's required. And then finally, this last question here is very similar, but this time we're going to actually solve for the volume of our gas phase product. So we're going to be kind of working in the opposite order this time. So here we're talking about the production of hydrogen using lithium. As an aside, this is why lithium batteries can sometimes pose a significant hazard, and we're talking about electric cars and other things that use them, because if lithium is in contact with water, it does release hydrogen, which is extremely flammable. So here's the unbalanced equation. We do have to balance this. Now technically this is a redox equation, so we could use the oxidation number method to do it, but this one's simple enough that we can just balance it by inspection. So I think the only thing we'll need here to make this balanced is, let's see, I think a coefficient of 2 there for water. That means we need a coefficient of 2 for lithium hydroxide and a coefficient of 2 for lithium. So that should be balanced. 2 lithiums on each side, 4 hydrogens, 2 plus 2, 2 oxygens. Looks like we're good. So this one was not too terribly difficult to balance, but if you wanted to use the oxidation number approach, you probably could have, but it wouldn't be the easiest one to do that way either. But however you choose to do this, we need a balanced equation. All right, and so then what we're looking for here is how many liters of hydrogen gas can be produced at this temperature and pressure when 3.75 grams of lithium reacts with excess water. So here we're going to do a stoichiometry problem first, and then at the end we're going to use PV equals nRT to find the volume. Okay, so let's do the stoichiometry part first. Let's first find how many moles of hydrogen are produced, because PV equals nRT involves number of moles, so that's going to be the quantity of the gas phase substance we want to solve for. Again, hydrogens are gas here. It wasn't indicated directly, but we're looking for, again, hydrogen gas. So the moles of hydrogen, we have 3.75 grams of lithium. We'll convert that to moles by using the atomic mass of lithium, which is 6.91. So once we have moles of lithium, then we can use stoichiometry to find out how many moles of hydrogen are produced. So 1 mole of hydrogen is a coefficient of 1 there for every 2 moles of lithium, which has a coefficient of 2. Alright, so when we work this out, I got 0.271 moles of hydrogen. So that's the amount of hydrogen in moles. What we're looking for is the volume, and so the relationship for gases that involves volume and number of moles is PV equals nRT. So now we have everything else we need to solve for volume. So volume is equal to nRT divided by P. We just found number of moles, temperature is given there, and pressure is given there. So we have volume, we have temperature, pressure, and number of moles, and we can solve for the volume that corresponds to. So number of moles we just found is 0.271. R is the universal gas constant. And then temperature is 18 Celsius, so we need to convert that to Kelvin by adding 273. So that's going to be 291 Kelvin. Make sure our temperature is in the right units. And then pressure needs to be in atmospheres. So we need to take this 725 and divide it by 760 to get atmospheres. So that's going to be 0.954 atmospheres. So atmospheres cancels out, moles cancels out, Kelvin cancels out, and that'll give us a volume in liters. And volume in liters is what we're looking for, so we'll stop there and just work out the numbers. And what I got was 6.79 liters. I don't remember, this one says don't type units, so I guess you just type the number as a numerical question. But again, if I didn't screw up the calculations anywhere, then that will be the number you get. But it's going to be sort of, as I said, the opposite process of the last problem. Stoichiometry first to find out how many moles of gas there are. Once we know how many moles of gas there are, we can combine that with the other given information in PV equals nRT to find the volume. Alright, so that takes me to the end of this week's review. So I encourage you to go through all those problems. They're pretty representative of the types of things we expect you to be able to do at this point. But if you have other questions on this homework assignment, please don't hesitate to get in touch with me. And I'll see you guys in class tomorrow.